So, again, I promise I will prove Euler's theorem later, but I want to talk about applications now. So, here's an idea. Maybe we can use Euler's theorem to decide if a graph is planar. So let's say we want to know if G is planar. Or I guess usually I'll use gamma, but gamma is just the Greek letter G. So this is my graph. Is it planar? Okay, and so here's something you might do. You might count V, E, F and decide if this is 2. And say, well, we know for planar graphs this is always 2, so if my graph isn't planar, so if this number is anything other than 2, then my graph isn't planar. Okay, sadly, if you think about it, this doesn't actually work because I only can figure out what the number of faces is if my graph is already planar, and I already know a planar representation of it. So sadly, this is not helpful. Okay, and so, in other words, I'm going to need to work harder to show that a graph isn't planar using this theorem. Okay, so I want to think about how I'm going to use the hypothesis that a graph is planar. And so the way I'm going to use the hypothesis that a graph is planar is I'm going to think of a planar graph with a planar representation. I'm going to think of it as a floor plan for a house. And in particular, I'm going to think of it as a floor plan for a house where each of these pieces is a room. So each face is now a room. And I'm going to imagine that these edges, of course, are the walls of the room. And I'm going to imagine that I'm painting the walls of the room. And I'm going to ask myself, basically, how many walls does my room have? Well, this room itself has 3 walls. That one, and this long one. Okay. And on the other hand, we have this room has 3 walls as well. And in fact, the outside face, it also has 3 walls. Okay, and so I'm going to take this idea, how many walls does our graph house have? On the one hand, every edge corresponds to 2 walls, one on this side and one on this side. So on one hand, the answer is definitely that it has exactly 2 times the number of edges. Okay. On the other hand, I want to think, what do I know about the relationship between the number of walls and the number of faces, or the number of rooms? Well, every room has at least 3 walls. Why is that true? Because I can't possibly make a bounded region out of 2 walls, because if I had 2 walls and I wanted it to be bounded, what would I have to do? I'd have to do this, but that's having 2 edges between the same 2 vertices, and we're expressly not allowed to do that. So every room has at least 3 walls, and so that means the number of walls, so this is number of walls. On the other hand, what I'm saying here is that the number of walls is at least as big as 3 times the number of faces. Okay, because again, every room has at least 3 walls. Okay, and this could be way bigger. For example, again, if you pull up the dodecahedron here, you'll see in the dodecahedron, every face actually has 5 walls, or every room in this floor plan has 5 walls. And so you might ask, okay, how does that end up working out? But it ends up working out anyway, because this inequality just becomes more true. Okay. So 3 is the minimum, could be more, but this is all we need now. And so what does that mean? Well, if I put these two pieces together, this means, this quantity, number of walls, it's exactly 2e, but 3 times the number of faces is less than that. So that means, here we go. So 3 times the number of faces is less than or equal to twice the number of edges. Okay. Now, in this case, in the K4 case, or the tetrahedron case, if you like, they're exactly the same. In this case, I had 4 faces, and I had 1, 2, 3, 4, 5, 6 edges. Remember, it was 4, choose 2. And so what we're saying here is that 3 times the number of faces, that's 12, is less than or equal to 2 times the number of edges, that's 12. So it actually really is less than or equal. It could be equal, or it could be way less. Okay. But keep in mind that my goal here is to decide if a graph is planar, ultimately, and I'm going to have a really hard time thinking about the number of faces to a graph that I'm deciding if it's planar or not. And so, remember, only planar graphs have faces, but if a graph is planar, then by Euler's theorem, sorry, wrong sheet of paper, by Euler's theorem, the number of vertices minus the number of edges plus the number of faces is 2, which means the number of faces is 2 plus the number of edges minus the number of vertices. So I'm going to use that. So namely, what that's going to tell me is that the number of faces is 2 plus the number of edges minus the number of vertices. And so in particular, what does that tell me? That tells me 3 times 2 plus the number of edges minus the number of vertices is less than or equal to twice the number of edges. And so continuing on, that says 6 plus 3 times the number of edges minus 3 times the number of vertices is less than or equal to 2 times the number of edges. Okay, and so I should then pull everything but the 6 over to this side. And so this is going to tell me that 6 is less than or equal to, and so now I'm going to get 3 times the number of vertices minus the number of edges. Okay, and so that actually gives me a theorem, because remember, I've done all of this calculation under the assumption that we're talking about a planar graph, right? Because I started by asking this question, okay, if I'm with a planar graph and I'm thinking about walls, what can I say about the number of walls? And so I did some reasoning from that. And so what this says is if gamma is planar, then, and I'll write this inequality the other way, 3 times the number of vertices minus the number of edges is bigger than or equal to 6. Okay, so just to do a couple examples of this, we can look at K4, Okay, so K4 has here 4 vertices, 4 faces, 6 edges. And so in this case, for K4, 3 times the number of vertices minus the number of edges. That happens to be 3 times 4 is 12 minus the number of edges, which is 6. So this is exactly equal to 6. 6 is greater than or equal to 6. Okay. Or if you want me to be more adventurous and try and deal with larger numbers, we can check this for the dodecahedron. Namely, we can look at this 20 and 30. And so for the dodecahedron, then what are we going to get? We're going to get 3 times 20 minus 30. And that is going to be 30. And that, lo and behold, that is also larger than or equal to 6. In fact, it's much larger than 6. Okay. Again, if you chase back through the proof that we gave of this theorem, then you'll find out, oh, hey, of course it's way better in the dodecahedron case. It's way bigger than the bound, because our whole proof was based on the idea that every room has at least 3 walls. But in the dodecahedron, every room ends up having 5 walls. So that makes this quantity way bigger. Okay. So there's our big theorem that's going to help us show that some graphs are not planar. Okay. So let's try the Peterson graph. So the Peterson graph we looked at before, we want to know if this graph is planar or not. And so we could calculate this quantity, 3 times the number of vertices minus the number of faces. And this number will work out to be 30 minus 15. So that's actually 15. That's greater than or equal to 6. And so that might make you think, oh, maybe this graph is planar. Maybe I have made a mistake. Okay. But notice this is an if-then statement. We don't know that the converse of this theorem is true. So we don't know that if this is greater than or equal to 6, then the graph is planar. Certainly we did not prove that. We started in our proof with assuming the graph was planar, and we got this. Now what we do know is we do know the contrapositive of this. So we know that if 3 times the number of vertices minus the number of edges is less than 6, that is, if it's less than or equal to 5, then the graph definitely is not planar. So here, we still don't know if the Peterson graph is planar or not based on this calculation. But this does actually work on one graph that we're on fairly good terms with. Namely, this will work for K5. Okay, so I want to think about K5. So first of all, let's draw K5 our usual way. So our usual way to draw K5, the complete graph on 5 vertices. Would look like this. Okay, so this representation of K5, to be clear, is definitely not planar, because if you look at it, the lines cross in a whole bunch of places. There are, I think, 5 total places where the lines cross. And so this is not planar, but I could certainly do better. And again, we sort of tried to do this before. So we said, okay, well, maybe instead of drawing this line like this, that's sort of unnecessarily making things cross, so I could draw it like that. Here's my K5 that I improved. So now instead of crossing in 5 lines, I only have this one. Okay, and so you could try and figure out, hey, could I redraw this in such a way that that crossing didn't happen? And feel free to try, but we should at least attempt our theorem So we should calculate for K5 3 times the number of vertices minus the number of edges. Okay, well, K5 has 5 vertices, so that's 15 minus... And how many edges does it have? Well, there's an edge between every pair of points, so the number of edges is 5 choose 2, which is 5 times 4 over 2, which is 10. Okay, so that is 5. That number is in fact less than 6. So the contrapositive of my theorem up here actually tells me that K5 is not planar. So by theorem, or by the contrapositive of the theorem if you prefer, by theorem, K5 is not planar. Okay. Now you might notice this is a pretty near miss. The thing I said was this number has to be at least 6. In this case, it wound up being 5. So you might say, okay, well, that kind of means that, well, there's, in some sense, one too many edges. So you might ask, hey, if I took an edge out of K5, would it then be planar? And if you look at our attempt here to make K5 as planar as we could, it's pretty clear that if I remove this edge, that number, or that graph that's left, is planar. And so K5 is not planar, but if you remove any edge from K5, any one of the 10 edges from K5, it then becomes planar. Okay. Again, that doesn't follow from the theorem, it follows from my picture here. That I've actually shown you how to make K5 minus one of its edges rendered inside the plane. Okay, so here is another graph that we want to know if it's planar or not. In fact, this is, I recall talking about in an earlier video, you might recall that I called this the utility graph, K33, the complete bipartite graph with 2 3s. And our question was, in some sense, whether we could connect the 3 houses on the one side with the 3 utilities on the other side without any of the utility lines crossing each other, which is exactly the question of whether this graph is planar or not. So you might count the number of vertices and the number of edges here and see if our theorem tells us whether this graph is really planar or not. So there are here 6 vertices and 9 edges. So 3 times the number of vertices minus the number of edges. That is, in fact, 3 times 6 is 18 minus 9. It's 9. 9 is at least 6, so our theorem is inconclusive. Okay, so that might make you think, okay, maybe this graph actually is planar. Maybe I just need to try and figure out how to draw it. So if you try and figure out, okay, if this graph is planar, well, here's one thing you could start with. If this graph is planar, so if K33 is planar, how many faces does it have? Okay, well, remember, vertices minus edges plus faces is always 2. So 6 minus 9 is minus 3 plus what is 2? Well, this would have to be 5. So if somehow I can draw this in the plane, then my number of faces here would have to be 5. Okay. But I want to make another observation. And this observation is very specific to this graph. Namely, because of the way my arrows work here, remember we have 2 different sides, and all the arrows here, or all the edges, connect something on the top to something on the bottom. There are no edges that connect something on the top to something on the top, and no edges that connect something on the bottom to something on the bottom. And so if I then think about how many walls one of my rooms could have, well, in all instances, if you go back to your favorite of the pictures we've drawn, the walls of a room, they form a cycle, right? So they form a path where you start at one vertex and then make it back to that vertex without repeating any. And so how many links are there in a cycle in this graph? Well, you're going to start at the top, then take one step and you're going to be at the bottom, and then another step and you're going to be back at the top. But you can't be back where you started yet because then it's not a cycle. So then your next step is going to take you to the bottom. Well, you can't be back where you started yet because you started at the top. And then your next step will take you back to the top. Okay, so now maybe now you've made it to the top. Okay, but what I've proven to you here is that every face of K33, if it's planar, has at least 4 walls. Okay, so there's 5 faces. Every face has at least 4 walls. So that would mean the number of walls is at least 20. Okay. On the other hand, I know how many walls there are because remember, every wall is half of an edge. It's one of the 2 sides of one of the edges. On the other hand, the number of walls is 2 times the size of E, which is in this case 18, because remember the number of edges of my graph here is 9. But whoops, 18 is not greater than or equal to 20. Okay, and so this is a contradiction to my attempt to make a planar representation. So this graph is not planar. Okay, so that is 2 graphs that we have shown are not planar, namely K33 and K5. Now, there's a big theorem that I'm definitely not going to prove, called Kuratowski's theorem, but I will state it for you and give you an example. And so what Kuratowski's theorem says is that basically those are the only 2 graphs that are not planar. In the following sense, a graph gamma is planar if and only if. Okay, so this really is a bidirectional implication. So if and only if gamma has no subgraph isomorphic to a subdivision of K5 or K33. Okay, so there are 2 words in here that I technically have not said. One of them I think is easier to guess what it means than the other. So what's a subgraph? A subgraph is some but not all of the vertices and edges of a graph. And so certainly, if your graph looks like this, except you've thrown in more pieces, so say I've thrown in an extra vertex here and connected it over there, and an extra vertex here and connected it there like that, and another one down here, this graph that I've now made, it has K33 as a subgraph. And I think you can convince yourself that because this graph has K33 as a subgraph, there's no way this graph could be planar. Because if I could draw this graph that I get by putting the black and blue edges together, if I could draw that in the plane, well, then definitely I could draw K33 in the plane, because I could just draw this graph with the black and blue edges in the plane, and then erase all the blue edges, and then I'd have a representation of K33. So one part of this is easy. Namely, if a graph has a subgraph isomorphic to K33 or a subgraph isomorphic to K5, then definitely it's not planar. Okay, so that part is easy because we've shown that those two graphs aren't planar. Okay, on the other hand, what is a subdivision? And a subdivision of a graph is a graph where or a thing where you start with a graph and you break up the edges of that graph by sticking new vertices in the middle. So I say, okay, well, this graph originally had 5 vertices. I'm going to put a vertex there, and maybe I'll go ahead and put 3 vertices here, and a vertex there, and 2 vertices on this one. And so I've now made a graph that instead of having 5 vertices, it now has something like 12 vertices. But again, if this graph suddenly had become planar, imagining I hadn't gotten rid of this before, then definitely I could unwind this all and just make a planar representation of this, and then just erase these dots again, and then I'd have a planar representation of K5. Okay. So that's what this theorem says. This theorem says that a graph is planar as long as there is no K33 or K5 hiding inside the graph somehow. And when I say hiding in, you have to look not just for the graph itself, but also subdivisions of the graph in the sense that you've added extra vertices along the edges. Okay, so I have teased one question that I've not actually answered yet, which is namely, I have teased the question of, is it possible to draw a planar representation of the Peterson graph? And I want to show you this very beautiful animation that I promise I did not make, but that is very beautiful. To show you, here's the Peterson graph. Okay, and we're going to throw some stuff away, and then we're going to remove some subdivisions, and then rearrange everything. And so what I've shown you here, or what, rather, I should say, the person who made this beautiful animation is showing you here, is that the Peterson graph, in fact, has a subdivision of K33 as a subgraph. And so if you play this animation exactly backwards, and you imagine you start with the K33, then you can see that what they're doing, again, looking at this animation backwards, is that they're starting with K33, they're subdividing it, and then adding some extra stuff, and that gets you the Peterson graph. And so by this animation here, our conclusion here is that if you believe Kuratowski's theorem, which you should because it's true, but if you believe Kuratowski's theorem, then in fact the Peterson graph is not planar. Okay, so I'll write that as a corollary here. Peterson is not planar. Okay, and again, that's true even though our bound about the number of edges and the number of vertices seemed to hold for the Peterson graph, but still, it's not planar. Okay. I'll encourage you, if you're interested, to try and come up with a better proof that doesn't rely on that to show that the Peterson graph is not planar. All right, we'll wrap up there for now. We'll pick up next time when I will really prove Euler's theorem for you. But until then, be well.